calculate only few of those rays, we're going to add a step to the to for loops. That means we'll intersect only every 10th pixel along X and Y. And if we would evaluate the script again, the result is, as you can see, every 10th pixel being calculated. And for every single ray, there is a tape created at the view position and pointing at the scene. Looking at the perspective viewport, you can see for every single pixel that was rendered, we can see the target point of the tape helper being created and visible there. We can delete everything that's called tape. And we could create an actual camera out of the viewport using the views. Create camera from view. We can see where the camera is. We'll change the step to 5 and evaluate again. And we'll get one ray for every 5 pixels. As you would expect, all these rays are inside the camera cone, and all the rays start at the camera position. Let's delete again. We can remove the step or set it to 1 and remove the tape creation. At this point, we should note that we rendered a single object and we never checked what would happen if there is an object behind or in front of this object. Let's create a sphere behind the teapot and try to render again. Contrary to what you would expect, the sphere is not rendered behind the teapot, it's rendered in front of the teapot because the sphere was created later and it's being intersected later inside this loop. That means that we'll have to add some Z depth, that means distance from the camera, measurement for every single intersection point that we're creating, and only return the color of the object that is close to the camera. Let's see how we can calculate the Z depth of every single point that we intersect and decide which point to return as a result of the array function. First, we'll need the viewport transformation matrix. The view TM is equal to viewport. As we know, get TM returns the viewport transformation matrix, which is the inverse of the transformation matrix of the camera. Then we'll also need a value, let's call it last Z depth value, and initialize to a very small value. Then, whenever we perform an intersection that is successful, that means we have hit a point on the surface, we're going to calculate how far this point is away from the camera position, from the eye position. To do this, we'll say Z depth is equal to the intersection ray, that's the first element of the intersection result, the position, this is the surface point that we intersected, multiplied by the view TM, and then taking from this point, which was converted into view space, we take only the Z value. If the Z depth that we calculated is greater than the last known Z depth, in this case we can say that the last Z depth is equal to the Z depth, and then we'll perform the rest of the illumination calculations. What happens here is the following. The farther an object is away from the camera, the lower the z value is going to be. That means we're getting negative z values, and the smaller the number, the farther away the point is. If the current point that we intersected is closer, that means it's greater than the last known z depth, in that case we'll set that value, the last z depth, to the current one. That means we'll remember that the current point was the closest one so far, and then we'll perform the calculations. If the point that we hit turns out to be farther behind, that means smaller than the last known point, then we're going to not perform any calculations on the lighting. For example, if we hit the teapot at this point, the teapot is the first object being processed. It's going to calculate the color. After comparing with the very, very small number that we have in the beginning, it's going to come to the conclusion that the current point is closer to the camera than what we know so far. It will calculate the lighting and store its z value into the last z depth variable. Then when we hit the surface of the sphere and the second pass of the O loop, the z value of the point of the sphere will turn out to be much smaller than the point on the surface of the teapot, and no calculations for the sphere are going to be performed at all. If we would evaluate the script at this point, we should get the sphere displayed behind the teapot and not in front.